Welcome everyone to the final seminar in our statistics department. And today is my great pleasure to have Iain, a postdoc from our department, to give a presentation about a couple of very exciting topics combining like a concave Laplacian spectral penalty and try to apply that to like block diagonal structures. And here, Iain is currently a postdoc in our department working with Daniela. And Iain received his PhD from UNC Chapel Hill and advised by Professor Bahmidi and Marans. And his research work on a couple of very exciting topics, including network analysis, image, and multi-view data. And he also has a lot of cool applications in genomics and computational pathology and the law. And today, he's going to talk about very exciting topic in the Laplacian methods. And just a reminder for all the audience, in case if you are not familiar with the format. So if you have any questions, you have three ways you can ask the question. You can either use the chat box, or you can type it in the Q&A section, or you can raise your hands and I will allow you to speak. So without further ado, let's welcome Iain.
Thanks, Yanchi. So the title is a bit of a mouthful, and hopefully hopefully the title will be demystified by the end of the talk. So to set the stage, we're going to think about learning with sparsity, and of course, we're probably familiar with a number of animals in the sparse model zoo. So sparse linear regression or GLMs, etc. And so a fairly common approach to learning with sparsity is take your loss function, add your favorite sparsity inducing penalty, a Lasso, for example, minimize that, and a large body of work has established that this sort of basic formula comes with very nice statistical guarantees. We recover, we can recover favorable estimation properties even in high dimensions, and it comes with nice computational guarantees. So often our loss function, our penalties are convex. And importantly, it's very easy to apply across many settings. And we kind of all know, if we're given a new loss function, we kind of all know what to do to make our estimate sparse. But sometimes we think there should be some structure in our sparsity. So the standard sparsity, I'll refer to entry-wise sparsity. But sometimes we think there should be some structure. So for example, the group Lasso says, well, I think that there's predefined groups of variables that should all be either in the model together or all zeroed out together or all in the model together. So maybe I think either my even variables should enter the model together, or my odd variables should enter the model together. And there's a variety of other structured sparsities. So the fused Lasso and other sort of Lasso generalizations. Or maybe I think my sparsity should be in the singular values of some matrix, the nuclear norm. And structured sparsity has a similar story to entry-wise sparsity. So take our loss function, add some structured sparsity inducing penalty, minimize that. And that often comes with similar appealing statistical guarantees and computational guarantees. And so our goal today is to add a new type of structured sparsity, or another type of structured sparsity, I should say, to the list, namely block diagonal sparsity. So for the rest of the talk, I'm going to first introduce what I mean by learning with block diagonal sparsity. Then I'll introduce our penalty, then talk about some of the general theory showing that our penalty works, and then illustrate that theory for a few classical estimation problems like linear regression, etc. So when I say a block diagonal matrix, we kind of all know what I mean by that, right? So there's one pictured here. And when I talk about, so we're going to talk about hollow symmetric matrices. So by hollow, I just mean all of the diagonal entries are zero. And in our setting, we're never really going to be interested in the diagonal entries anyway. So right here, so I'm showing you right now a block diagonal hollow symmetric matrix. And you should kind of think of this as an adjacency matrix to sort of orient yourself to where we're going. But what we're really going to talk about today is block diagonal sparsity up to permutations. So the matrix on the left is we would all agree that's a block diagonal matrix. And on the right, we wouldn't, doesn't look like a block diagonal matrix per se. So all I've done to go from left to right is permute the rows and columns by the same permutation. And we're going to say that those two matrices are in some sense equivalent. They're sort of block diagonal up to permutations. And so block diagonal property can apply to matrices beyond symmetric matrices. So here's a picture of a rectangular matrix. And our methods will cover or can be extended to cover rectangular matrices. And we can even talk about block diagonal multi-arrays. I'm not going to define this precisely, but again, our methods will sort of naturally extend to the multi-array case. So to think about what block diagonal sparsity up to permutations mean, really the natural setting is to think about graphs. So we're going to say, and I'm going to be somewhat informal, a vector has block diagonal sparsity up to permutations. If we can take that vector, view it as the edges of some graph, and that graph has multiple connected components. So I'm going to abuse notation a little bit. So our vector probably has real valued entries. And so that the graph has real valued edges. And so when I talk about connected components of a graph, I mean connected components of the support graph, right? Create the corresponding binary graph that's either 1 or 0, and the connected components of that. But I'm just going to talk about connected components. So for example, say I have a correlation matrix and beta on a correlation matrix on D variables, and maybe beta is the upper triangular elements of that correlation matrix. And so if that correlation matrix is block diagonal or could be permuted to be block diagonal, then we would say that the vector of upper triangular elements of that correlation matrix has block diagonal sparsity. Right, so for this graph, the nodes would be the variables, the edges would be the correlations, and the blocks, of course, would be the connected components of our block diagonal correlation matrix. So the three graphs I've shown you have, the two matrices in an array I've shown you all have 4 blocks, or they all have graphs they have corresponding graphs who have 4 connected components. And I've only told you what the graph is for the symmetric guy, and we're just going to focus on the symmetric setting. So this has 3 sort of non-trivial or non-zero blocks, and then a 4th isolated vertex, or a 4th row of zeros or columns. But we're going to call that 4 blocks for our purposes today. And so for pretty much the whole talk, for the rest of the talk, we're really going to focus on hollow symmetric matrices. But as I mentioned, all of our methods will extend naturally to the rectangular multi-array case. And so to explicitly state the context of our learning problem is our goal is to estimate some parameter vector beta, and beta is going to be d-choose 2-dimensional. I'm going to assume we can somehow view beta as the edges of some graph. So again, maybe beta was the correlations, and we could view we can map the correlations to the correlation matrix, and that gives a graph. So beta is the upper triangular entries of some hollow symmetric matrix. And there's going to be we're going to talk about our goal is to estimate some target parameters. So that could be, for example, the population coefficient, the population correlations. And we're interested in the case that we think our target parameter has block diagonal sparsity. So we think that the true population correlation matrix is block diagonal. So I should just state an abusive notation explicitly. So I'm going to equate adjacency matrices with graphs. So I'll talk about matrices having connected components. And I'll refer to the following 3 quantities exchangeably sometimes. So our vector of beta of upper triangular elements, or its corresponding hollow symmetric matrix, or its corresponding graph. So I might say beta has 4 connected components, or its adjacency matrix has 4 blocks. So what are some example statistical models where this might come up? So of course, in correlation or covariance matrix estimation is a very natural setting for this, at least in the Gaussian case, when we might think that we have groups of variables that are associated with each other, but independent across groups. Or maybe we're working with linear regression where our coefficient vector can be somehow mapped, can be somehow viewed as the edges of a graph. So maybe we're solving a regression problem where I've stuck you in a, I don't know if it would be an MRI, some brain scanning machine. And the response is, how engaged you are in this lecture. Our graph is going to be, let's say there's D regions in the brain. And let's say we can monitor the amount of activity or the amount of blood flow between the regions of the brain. So right, that gives us some graphs. That would be our X data. And we could solve a regression problem trying to use the connections between the regions of the brain to predict our response. And so maybe we think only connections that are within some regions are related to the response. So maybe maybe it's really the things that are going on within the left hemisphere of your brain and things that are going on within the right hemisphere, but not between the two hemispheres. So that would be an example where the population quantity would have a block diagonal structure. Or maybe we're talking about a multiple response regression where our response is in C covariates. And we think that let's say here's beta is our regression coefficient matrix. And maybe we think, only some of the covariates are associated with some of the responses. So that would be an example of block diagonal sparsity with a rectangular matrix. So hopefully we can all agree that this is an interesting statistical problem to look at least in some cases. And it should immediately remind you of community detection, where it's reminiscent of community detection, but it's not quite the same thing. So in community detection, we observe some graph, and we want to estimate communities, which are some kind of like nodes that are densely connected within each other and sparsely connected across communities, something like that. And so in community detection, the edges are known. We observe the edges. And nodes between communities can have edges. So communities don't have to be perfectly connected. So, however, in our context, our goal is to simultaneously learn both the values of the edges and the connected component structure of the graph. So in particular, our edges are unknown. But we impose the stronger assumption that nodes between connected components cannot have an edge. It's also somewhat reminiscent of group Lasso, where in group Lasso, we think there's pre-specified, we pre-specify some groups of variables that we think should all be maybe zeroed out together. And so learning with block diagonal sparsity is something kind of similar, but we don't specify the groups of variables ahead of time. But we also require the groups to have sort of some block structure. So there's a growing literature on estimation with on block diagonal estimation. There's a lot of the papers are focused on covariance matrix estimation or precision matrix estimation, but it comes up in a lot of other places. And so my motivation for this talk was the paper that I talked about last year on multi-view clustering when I had a similar block diagonal estimation problem come up. And my goal sort of after that paper was to study the statistical properties, or give some kind of guarantees to learning with block diagonal structure. So the summary of the contributions of this project is, first we're gonna develop a general framework for learning with block diagonal sparsity, and by that I mean we're gonna develop some penalty, the folded concave Laplacian spectral penalty, that you can just throw on, hopefully any loss function, and it, hopefully returns the block diagonal structure you wanted it to. Our method is going to be computationally tractable, so we're going to develop a majorization minimization algorithm that is friendly subproblems. So by that I usually mean they have convex subproblems. And we're actually going to provide very strong computational guarantees. So our guarantee is going to say with high probability, assuming our conditions are met, that our MM algorithm converges in exactly 2 steps. So there's no, so that's about as strong as guarantees you could ask for. Of course, assuming our conditions are met. And maybe more interestingly, because we're in a statistics department, we can provide some appealing statistical guarantees for the estimate that's output by the MM algorithm. So we're not talking about any kind of global minimizer that we are probably never going to be able to find. We're talking about the actual output of the algorithm. And so in particular, we're going to recover something that I'm going to call the block oracle with high probability. So if you're familiar with the strong oracle property from standard sparsity, we get something like that. And I'll define this precisely a little bit later. So we're going to provide some general theory, and then we're going to show how that theory plays out for a number of classical statistical models, such as a Gaussian sequence model, covariance estimation, linear, and logistic regression. All of our guarantees are going to be non-asymptotic, and they're usually going to work in ultra high dimensional settings, when you have maybe an exponential number of features in the number of samples. And so our method is going to take two ingredients. So first is some spectral properties of the graph Laplacian, which probably a lot of people are familiar with, and I'll review a little bit later. So using these kind of using some of these spectral properties of the graph Laplacian, there's a number of existing approaches that incorporate the spectrum of the Laplacian to learn block diagonal structure. And our method is going to be related to those, but it's not the same thing. And our theory doesn't literally apply to many of these papers, but it should be transferable with not too much work to several of them. And I should say, at least to my knowledge, there's like zero statistical theory for learning block diagonal structure in general. There are particular cases, particularly in covariance estimation, where there are some statistical guarantees, but definitely not for these Laplacian methods. And there's also, typically fairly weak computational guarantees for these Laplacian optimization methods, like eventual convergence to a stationary point. So that's our first ingredient, the spectral properties of the graph Laplacian. And our second ingredient is going to be folded concave sparsity inducing penalties. So, we're probably all familiar with the Lasso, and maybe many of us are familiar with the Lasso has some concave generalizations, such as the smoothly clipped absolute deviance, whatever, the SCAD penalty, which is some kind of concave version of the Lasso that can have sort of more favorable estimation properties than the vanilla Lasso. And so this project is inspired particularly by this paper from Zhengchen Fan et al. In 2014 on the strong oracle property for sort of entry-wise sparsity. Okay, so let's dig in. So now we're going to talk about what is this penalty that I've been hyping up so much. So to set the stage, if I was trying to sell you on learning with sparsity, you came to me with some loss function, I would say, hey, I'm going to solve this amazing constraint problem, where I minimize your loss function. I'm going to constrain the vector to have, not too many non-zero entries. And of course, as sophisticated statistical consumers as you all are, you would say, hey, it's probably computationally intractable, which of course it is usually. And so we're actually going to solve some penalized problem. We're going to throw some sparsity inducing penalty on our loss function. And so we're going to follow this sort of same outline for learning with block diagonal sparsity. So we have some loss function and some coefficient vector beta. And remember, beta is always going to be D choose two-dimensional. And we're going to assume we have some way of viewing beta as the edges of a graph, or the entries of the upper triangular entries of a holosymmetric matrix. I'm going to minimize our loss function subject to the constraint that our graph has k connected components. And so here k, of course, controls the level of sparsity, and setting k to be larger means that we have a more sparse solution. So if k is exactly equal to d, the number of nodes in the graph, we get the zero vector. So of course, we probably can't solve this problem. So we're going to solve some penalized version, where S is going to be our Laplacian penalty. So what is the graph Laplacian? So the graph Laplacian takes an adjacency matrix A. So by adjacency matrix here, I mean A has to be positive and symmetric. That's it. And it has zeros on the diagonals. And I'm going to take the row sums of that matrix, throw that into a diagonal matrix, and then subtract off the adjacency matrix again. And that's our graph Laplacian that probably many of us have learned about. So there's just a couple of properties of the Laplacian that we need. So first, that it's a symmetric positive definite matrix. But critically, the number of 0 eigenvalues of the Laplacian is exactly equal to the number of connected components of A. So that's the first critical insight that we're gonna work with. And the second observation is that the eigenvectors corresponding to those 0 eigenvalues encode the connected component structure of the graph. So if you take the kth eigenvector corresponding to a 0 eigenvalue and look at the jth entry, that's going to be some non-zero number if node j is in the kth connected component of the graph, and it's going to be 0 otherwise. So visually that looks something like this. So if I take the graph on the left, here's its spectrum. So I told you this graph has 4 connected components. So we see 4 0 eigenvalues. And then here are the corresponding eigenvectors. They look like the indicators. Great. So now we're ready for step 1, which is we can now equate the constraint, the combinatorial constraint that our graph has at least k connected components, with the continuous constraint that the Laplacian of our graph has k eigenvalues equal to 0. And importantly, I'm going to take entry-wise absolute values on our beta vector, right? Because the sort of nice spectral properties of the Laplacian require the adjacent matrix to be positive. So absolute value of the vector, map it into an adjacent matrix, then compute the Laplacian, and constrain that to have k eigenvalues equal to 0. And so to ease notation a little bit, I'm going to write mathcal L to be beta to be the composition of the Laplacian and the adjacent matrix. So L of beta is just going to be the Laplacian. Okay, so step 2. Well, the natural thing, the most obvious thing to do is just penalize the sum of the eigenvalues. Lasso the spectrum of the Laplacian, right? So for example, we might be familiar with the nuclear norm, which is a way of inducing sparsity on singular values. The nuclear norm basically does this, penalizes the sum of the eigenvalues. But there's a problem. Because our Laplacian matrix is symmetric, we end up, if we do this, we just end up back at the lasso. So you can check pretty easily that the sum of the Laplacian eigenvalues is just going to be exactly equal to 2 times the lasso penalty of our vector. So it's not the lasso is of course a reasonable thing to do for sparse learning, but we haven't taken anything about the fact that we're learning a graph, or we're working on a graph. We haven't taken that into account. So can we do better? And the answer is of course yes. And the idea is to, instead of sum the raw eigenvalues, pass the eigenvalues through some nonlinearity before we sum them. So in particular, I'm going to take some concave function g, should be concave and increasing. So think like an LQ, square root, or LQ norm, or maybe the SCAD function. I'm going to take our vector, compute the Laplacian eigenvalues, pass that through our concave function, add that together, and that's going to be the folded concave Laplacian spectral penalty. And I'm going to write it as g composed with lambda to ease notation in the sequel. And so an important factor of this penalty is so S is not a convex function. It's not even a concave function, but it's concave in the absolute value of beta. And so in the literature, this is why we call it a folded concave, or where the word folded comes from. So S is concave in the absolute value of beta, and that's also going to play an important role for estimating, or for our algorithm design. So to summarize, we're going to solve the following penalized problem. Take our loss function, add our Laplacian penalty on it, and our penalty function g is going to have some parameter tau, and tau is going to control the level of block diagonalness. And so like Lasso penalized problems, this penalty can give you exact zeros in its solutions. But as I mentioned, that this penalty is not convex. So what do we do? we're going to apply a majorization minimization algorithm. So I'm just going to give a brief background on majorization minimization. So the goal of majorization minimization is to minimize some function f, and say f is some kind of nasty function that we don't we struggle to work with. Well, we're going to replace f with some maybe nicer function q that I'm going to call a surrogate function. And our surrogate function has to satisfy two properties. So namely that, I should say the way majorization minimization works is we take our current guess and we construct this nicer function q. So say y is our current guess. We're going to construct some function q given y. And so q of evaluated at x should be exactly equal to f of x. And but for all other values, q should be at least as large as f of x. And I'll show a picture of this. So the picture looks like this. So f is our blue function, which is some unfriendly function. Q is going to be our surrogate function. So let's say our current guess is right here. Our surrogate function should be equal to f at the current guess. It should be greater than f at sort of everywhere else, which of course this red function is. And so given our surrogate function, we're just going to minimize the surrogate function, and that's how we're going to update our parameters. So in other words, the majorization, an MM algorithm takes some initial value, constructs the surrogate, and then minimizes the surrogate to get the updated value. And it just repeats until you converge on a stationary point or something. So here's the picture. And so we're going to use an MM algorithm on our Laplacian penalties. So the first thing we use is a surrogate function. And so it turns out that although our Laplacian penalty is defined through some minimizing some concave function of eigenvalues, it has a surrogate function that's given by a weighted lasso, or I should say a positively weighted lasso. So this is a convex thing. So in fact, our majorization minimization function has a surrogate function that looks like this, where these weights m are going to depend on our current guess. So let's say little b is our current guess. We're going to compute some weights. We're going to call them m. And those, I'm not going to tell you right now, or I'm not going to tell you exactly what the form of m is, but it has a closed form that's not too hard. But it's a function of two things. So given our current guess, I'm going to compute the eigenvectors and eigenvalues of the Laplacian of our current guess. And I'm going to pass the eigenvalues through the gradient of our concave function. And so that's sort of the main part of the majorization step. And so given our current guess, I compute an eigendecomposition of the Laplacian, compute our surrogate function weights. And then once we have our surrogate function, we minimize it. And that's how we update our parameters. So in other words, our MM algorithm alternates between eigendecomposition and then solving a weighted lasso problem, or our convex weighted lasso problem. And so this there's a number of existing papers that do similar things for entry-wise concave penalties, and they call this the local linear approximation algorithm. So in the spirit of some of this existing literature, I'm going to refer to this as the LLA algorithm, the local linear approximation algorithm. Okay, so hopefully by now I've convinced you that the folded concave Laplacian spectral penalty is a reasonable thing to try to do to learn block diagonal sparsity, and hopefully I've convinced you that we have an algorithm that will maybe find a stationary point or something. Typically, majorization minimization algorithms are only guaranteed to find stationary points, but it's going to turn out that we can provide better guarantees than that. So I'm going to make two assumptions going forward, or sort of two main assumptions. I'm going to hide all the minor technical assumptions under the rug. Our two main assumptions is that the loss function is convex, and that the concave function that we use g is what I'm going to call a SCAD-like penalty function. By a SCAD-like penalty function, I mean something that looks like this. So it's here I'm plotting the penalty as a function of the absolute value of x. So for small values of absolute value of x, the penalty function looks exactly like a lasso. So here I've plotted here, that's the lasso-like region. This penalty function takes two parameters, tau, so that's going to be the weight that we tune, and it takes it's called a hyperparameter alpha that's fixed ahead of time. It's for SCAD, it's usually fixed to the magic value of 3.7, but anyway. So for small values of absolute value, for small values of x, a SCAD-like function looks exactly like a lasso. For large values of x, the SCAD-like function is completely flat. And for intermediate values, it's some concave function, and the details of that are not too important. So a draft of this paper is going to show up on arXiv fairly soon, and you can see the precise details of this on the draft. So we're going to assume that we have a SCAD-like penalty function, and the sort of critical part of the SCAD-like penalty function is that we have this flat region. Now I need to introduce a couple more technicalities. So if I give you a vector, we can all agree on what the support of that vector is, and I need a slight generalization of the support, which namely is the block support. So let's say beta, our vector beta, is the upper triangular entries of this matrix on the left. We can here the white squares correspond to 0 and the gray corresponds to non-zero entries. And we could all agree that the support is these gray entries. So the size of the support is 9. And the block support, which I'm not going to define precisely, but all the block support means is we're going to fill in the within block edges. So namely just this guy here. So in other words, the block support of beta would have cardinality 10 instead of 9. Okay, so now we finally reached the sort of one of the main quantities of the paper, which is the block oracle estimator. So to set the context, we're going to have some target parameter that we're trying to estimate. So just think of beta star as maybe the population parameter. So maybe it's the population correlations in a correlation learning model. And that population parameter has some block diagonal structure. In particular, it has some block support. I'm going to write that as S star. And our population parameter, we're going to say has K connected components. And so the block oracle estimator is the solution to the following minimization problem. Minimize our loss function subject to the constraints that the between block edges are 0. So in other words, we zero out in other words, the block oracle estimator knows the true support set, or at least in this case, the true block support set. And so of course the target parameter is a quantity. An algorithm is probably not going to ever output exactly the target parameter, but an algorithm can output the block oracle estimator. And so the strong oracle property means that that if we have some estimator, that estimator outputs exactly the block oracle estimator with high probability. So that's the strong oracle property. And we need one more quantity, which is the target spectral gap. So remember, our population parameter has K connected components, so does K eigenvalues equal to 0. And the target spectral gap is just the size of the K plus first smallest eigenvalue. And so the target spectral gap quantifies the signal strength of the blocks. It sort of plays the role that if we were looking at a regression problem, that the smallest non-zero entry of the coefficient would play. And so to gain a little bit of intuition on the target spectral gap, we have the following inequality, namely that say we have some graph and say that the smallest non-zero connected component of that graph has d min nodes. The target spectral gap is equal to d min times the magnitude of the smallest non-zero entry of that graph. So really the main point here is that larger connected components sort of implies a more visible signal. So you could hold beta min fixed and increase d, and your signal should hopefully become stronger. So now we're going to provide some general theory to answer two questions. The first one is, when is the block oracle a stationary point of the Laplacian penalized problem? So this is maybe not the most interesting thing in practice, but it's sort of, if our algorithm doesn't have this if the answer is no to this, then we kind of sort of hopeless. And then the second question is the more interesting problem, which is, when does the LLA algorithm initialize by some initializer, and the initializer is going to be important. When does the LLA algorithm converge the block oracle in exactly 2 steps? And so that's going to be the question of central interest. And I should contrast this with standard entry-wise sparsity folded concave penalties, where there's a similar methodology with LLA algorithms. And for those, you only need 1 step, but we need 2. And so our affirmative answers are going to come in 2 stages. So first, we're going to find some deterministic conditions on the initializer, the oracle parameter, the loss function, etc. And then for particular statistical models, we're going to verify that those conditions hold with high probability. Okay, so how's this going to work? Well, taking a step back, the main sort of quantity of interest is, or object of interest is, what happens when you take an LLA step from some current guess, little b. So remember that our majorization minimization algorithm updates the parameter by solving these Lasso penalized problems, where the Lasso coefficients come from our current guess b. And so what we would like to be true is that if we look at our target graph, what we want is to penalize the edges that go between blocks in our target graph. We want to penalize those a lot, right? Because we want to kill those edges. But for the edges that go between nodes within a block, we don't want to penalize them. Ideally, we don't penalize them at all. So we want to be able to make some statement that our Lasso coefficient is small on within block edges, and it's large on between block edges. So that's our goal. And you'll have to see the paper for the details of how we do this. But I can summarize the main ingredients. So namely, we have an analytic formula for the Laplacian weights M. And that formula depends on the eigenvectors of the Laplacian at our current guess, the eigenvalues, and namely the gradient of our concave function evaluated at those eigenvalues. And so if you remember, I said that the SCAD-like functions have a flat region. So in other words, if we have large eigenvalues here, this gradient might be equal to 0. So that plays a sort of central role in the theory. We'll also need, sort of standard properties of the graph Laplacian and SCAD-like penalties. And we're going to use Davis-Kahan to sort of talk about, eigenvectors being close together. And we're going to need sort of the sort of main quantity of that we're going to need is we need a good initializer. And by good initializer, I mean that this ratio right here is not too big. And so on the top of this ratio is our initializer. And then we're saying, okay, hopefully our initializer is close to, is close-ish to the target parameter. And then, compute the Laplacian of that operator norm. And we're going to divide by the target spectral gap. So if the target spectral gap is very small, then that's going to make our problem a lot harder. Or if it's big, conversely, that makes our problem a lot easier. So we're ready to present our first result. and this is, so say we start the LLA, or say we take an LLA step from some point beta naught. And let's make the very strong assumption that the beta naught, the block support of beta naught is a subset of the target graph's block support. So beta naught essentially knows the true support. If we have some technical, and we're going to assume some technical assumptions hold. And the conclusion of our result is going to be that taking one step from beta naught is going to result in exactly the oracle estimator. So this would be the one-step convergence version of our theory. And so we're going to need two other conditions, namely that our initializer has sort of k well separated enough blocks. And then we're going to need some condition on the gradient of our loss function that basically says that between block edges are killable. And so this theorem has two implications. So first, it gives conditions when the oracle is a stationary point of the Laplacian spectral, the Laplacian penalized problem. And so this answers our first question. And it also gives conditions for one-step convergence of the LLA algorithm, but it gives pretty stringent conditions. And so, by taking two steps, we can relax our conditions to be a little more reasonable. And so before we do that, I need to define one more concept, which is the solution set of weighted lasso problems where the weight vector is not too big. So in other words, if you give me some weight vector W, I'm going to solve the following lasso oracle problem. So I'm going to solve this. It's a loss function plus a lasso term, and I'm going to constrain my my target, the between edges of the target graph to be 0. So this constraint is why I call it an oracle lasso. And then I'm going to define the set beta sub rho to be all the beta such that beta is a solution to some weighted lasso oracle problem where the weight vector is not too big, where not too big is measured by the sup norm of the lasso coefficient. So that's just some set of our D choose 2. So now we're ready to present the theorem. So let's say we initialize the LLA algorithm at some point beta naught, and some technical assumptions hold. We're going to get two-step convergence to the oracle, and so we're going to need a few more meaningful conditions. So first is that our initializer is sort of close enough to being k block diagonal, so that there has to be some evidence that of the graph's sort of true structure in beta naught for the Laplacian to be able to do anything. This is a condition I sort of talked about before, namely that our initializer is sort of close enough to the target gap, where this is the quantity we use to measure close enough. And then we're going to need two regularity conditions that are sort of similar to the conditions in the previous theorem. We need two regularity conditions to hold for every element of beta sub rho. So remember, beta sub rho was the set of weighted lasso solutions, and so we need some regularity conditions to hold for every element in that set. So if all of these conditions hold, then we get exactly two-step convergence to the oracle. So this is the deterministic version, and this is of our main result. And now I'm just going to sort of restate it in probabilistic language. So let's suppose some technical assumptions are true, and let's assume that our target gap is some constant times our tuning parameter tau. Remember, tau is the tuning parameter of the Laplacian penalty. Then the LLA algorithm initialized from beta naught converges to the oracle in two steps with probability at least 1 minus a few terms. And I can give you explicit expressions for all of these terms. So in other words, we need the probability that we have a good initializer to be large. We need the probability that some regularity condition related to the gradient that's nice enough to hold, and then we need some other regularity condition related to to a certain Laplacian residual to hold. So this gives us a roadmap for applying our theory to particular statistical models. So in particular, we have to control these three quantities. And so this is where the sort of probabilistic part of our paper would start. Namely, that we have to be able to have a good enough initializer. And so often we can apply just sort of standard results, maybe about like the estimation accuracy of a lasso to control terms like this. And then maybe we need to do a little bit more work to control some of these other terms. But let's see what happens when we apply our general theory to some particular models. So the first model I'm going to think of is maybe the simplest statistical model you could think of. And so our loss function is going to be the Frobenius norm. But we're going to motivate this as follows. Let's say we have some OK estimator of the population parameter. So maybe beta OK is the sample covariance matrix. It's not a horrible thing to do. It might not work super well in high dimensions, but let's say we have some OK estimator. And so a very standard idea from sparse estimation is let's take our OK estimator and let's just shrink it towards 0. So we know a priori our target parameter should have a bunch of zeros. So let's take our OK estimator and throw in some zeros. And the way this is usually accomplished is by applying maybe a hard thresholding operation to the OK estimator or some generalized thresholding operation. And so thresholding operations, if you're familiar with the language of with proximal operators, thresholding operations are normally just the proximal operator of some penalty function. And so we're going to try to do something that I'm going to call block diagonal shrinkage. So in other words, given our OK estimator, we're going to try to compute the prox of the Laplacian spectral penalty. Or something like, given our OK estimator, let's find like the nearest block diagonal matrix. So we're going to try to solve this optimization problem here. And so, of course, we probably can't exactly solve it, but we can apply the LLA algorithm. But before we do that, we need just a couple of we just need one major assumption on beta OK. So beta OK has to be, truly some not horrible estimator. So let's assume for now that beta OK has sub-Gaussian tails after observing n samples. So, and by that I mean that the difference between the absolute difference between each entry of beta OK and our target parameter has sub-Gaussian tails. It's this deviation is bounded by some Gaussian. And so some example models where this comes up would be probably the most simple statistical model, which is a Gaussian sequence model. So in a Gaussian sequence model, I observe n IID observations. And the true model is just take the mean and add some normal noise to it. And our OK estimator is going to be just the sample average. In covariance estimation, you can take my word or read some of the references in the paper. The sample covariance matrix has sub-Gaussian tails. And so maybe in this case, beta OK would be the upper triangular entries of the empirical covariance matrix. And a lot of other models have this property. And so how do we initialize? Well, it turns out the initialization strategy really matters. So maybe the most natural thing to do is initialize at beta OK. As that's going to turn out to succeed, we can show it succeeds in low dimensional settings, but it doesn't necessarily work in high dimensional settings. 0 is another reasonable place to initialize from, but that turns out can work in theory, but it doesn't really work in practice. But what we're actually going to initialize from, or what's going to work the best, is let's take our OK estimator and let's apply some shrinkage operator to it. So hard thresholding. So let's get some initial, decent estimate. Let's take our OK estimator and get, a better estimator. And then let's initialize our LLA algorithm from there. And it's going to turn out that this will work in high dimensional or even ultra high dimensional settings. And so we're going to end up with a result that looks like this. So let's consider the Gaussian sequence model, and let's just assume that all the connected components of our target graph are fully connected. Then under this condition right here, the LLA algorithm initialized from an appropriate hard thresholding estimate will converge the oracle in 2 steps with high probability. So taking a look at this term right here, the dimension enters logarithmically. So that's why this succeeds in ultra high dimensions. And we have this term Q star here. So Q star is the size of the connected components. And so slightly weaker statement holds. So this statement is for the Gaussian sequence model, but a slightly weaker statement holds for just sort of general sub-Gaussian residuals. And so this is what we've shown in the manuscript, and it's possible that stronger guarantees are going to be possible, and I'll show some simulation evidence that that's true. So it's an open question of, can we actually obtain better guarantees? So in particular, what's the role of Q? What I think is true is that Q should disappear, or probably Q should actually be on the denominator of this term. And so if Q is on the denominator of that term, that means larger blocks make the learning problem easier for the Laplacian penalty. I guess I'll go through these next slides fairly quickly, but the basic story that I just told you is going to be true for linear regression. So if we have the standard linear regression setup, and we initialize from an appropriately chosen Lasso estimator, then the LLA algorithm obeys the strong oracle property, even in ultra high dimensional settings. And again, the same story is going to be true for logistic regression. Although for logistic regression, the proofs are a little bit more involved. And so now let's look at some simulations. So hopefully I've convinced you that at least in theory, these methods work. I haven't necessarily convinced you that these methods are better than maybe competing methods, but let's see what some simulations have to say. So I'm gonna run simulations for each of the models that I just talked about. So Gaussian sequence model, covariance estimation, linear regression, etc. I'm gonna look at 4 different graph topologies. So the first one, beta is in all of them. There's going to be 2 equally sized connected components. So the graph of beta will look something like this, and I'm just going to change the number of nodes. So it'll be first one's 5 nodes, second one's 10, etc. I'm going to fit our models sort of across the range of tuning parameters and pick the best tuning parameter to report the results. So this is sort of, from a methodological standpoint, this is cheating, but it's sort of it's a reasonable thing to look at to evaluate the estimator. And I'm always going to initialize our models using the 10-fold cross-validation of a Lasso initializer or something like that. So let's take a look at what happens. So here's the Gaussian sequence model, and on the x-axis is the number of samples. So as you get more samples, the problem becomes easier. And the y-axis is the distance to the oracle estimator, or really the relative L2 distance. So we normalize by the norm of the oracle. And the thing to look at is this blue curve right here is the results of the Laplacian spectral penalty. And so we can see the Laplacian spectral penalty does the best. The yellow curve is the hard thresholding operator, which would sort of be the natural competitor for this problem. And the green curve is going to be just the empirical, the means empirical mean. So here are the results for the 5-node model, and for the 10-node graph, and the 25-node graph, and the 50-node graph. So the takeaways from these simulations is, really in short, is the Laplacian penalty does work, and it works sometimes significantly better than just hard thresholding. And so the sort of rough takeaway from that simulation is going to be true for all of the other models. So here's, for example, the covariance model. It'll be true for linear regression, and the logistic regression models is the simulation is still running, so I won't show you any curves. And And so I'm going to stop. I'm going to conclude the talk there. And I should say there's a lot of follow-up questions here. So I think most interestingly is maybe a sharper analysis. So I don't think it's obvious how to improve the current analysis, but I have sort of a lot of ideas for maybe how we might be able to do that with some work. And if anyone's interested in working on extensions of this, feel free to reach out.
Okay, thanks, Ian. Very exciting talk. And any questions from the audience? And actually, I myself have two quick questions, and I just probably more like making sure that I understand the idea, the main idea correctly. So the first question is that, so you mentioned that when you use this GTAL, you use a SCAD-like penalty, right? So I guess that's the intuition. Is it the intuition that we actually only need this penalty to encourage sparsity, but we actually don't want to penalize a very large value of lambda because it actually doesn't really matter that much in the later constructions?
Yeah. So the motivation for like concave penalties is to really penalize the small values and not really penalize the larger ones. Yeah, that's right.
Okay, great. And I have another question about when you are talking about this good initializer, and then you have a couple of very nice theoretical bounds on that. And I think I noticed that it seems that because I think if you go to the page 14, I think you have the Boolean item 1 and 2. They are the two key conditions that you.
Sorry, you said go to page 41. Yeah,
I think at page 41, I think you have mentioned like two key conditions of what. Oh yeah, I think 41. Yeah. Right. I think this point 1 and 2 are like the two key conditions you need a good initializer, right? So
yes, exactly. Yeah.
Right, and I think later on I saw that you have a lot the probabilistic bound is mostly for the point the second part, right? That's where you get these probabilities.
So so for the sake of exposition, I just kind of combined it all into one. But the statements in the paper will have one of the terms will be the probability that your lasso works well enough. Yeah.
I see. So you need basically you need an initializer to have a similar block, at least to a certain extent the similar block structures, right?
Yeah. And you see stuff like this a lot in non-concave or in places where you get statistical guarantees for non-concave optimization problems. Sorry, non-convex optimization problems that you initialize it with something that's probably the solution to a convex problem, and then hopefully that was roughly in the ballpark. But then when you solve at least the approximation of your non-convex problem, then you get very, very nice properties. Yeah.
Yeah, I see. I'm also curious, although with this theorem is saying a very powerful result, converging two-step. So I'm curious that even if you have that, have you tried maybe in simulations or something, you purposely choose an initial point that's not so great, but it could. Is it converging also fast?
So okay, when you're the convergence will really depend on how the signal to noise ratio. So if the signal to noise ratio is really high, if your problem's really obvious, then you'll converge immediately. For harder problems, then, or maybe to state this differently, is we could look at the two-step LLA algorithm, or we could look at the output of the LLA algorithm after it's converged, run it for 1,000 steps. And sometimes, particularly in the harder regimes, the convergent version can be you can squeeze a few more accuracy points out of it with the fully convergent. And I think that'll be one of the interesting theoretical questions, is the theory for the K step or the fully converged. But you can't really initialize it from anywhere. I haven't tried sort of from anywhere, but the theory will say that 0 can sometimes be a good initializer, but in practice 0 is not a great initializer. But yeah.
I see. Okay, and other questions from the audience? Oh yeah, there's a question from Daniela. Okay, let me allow. Yeah. Okay. Yeah. Daniela, I think you should be.
Can you guys hear me now?
Yes, I can hear you.
Yeah, I guess I'm wondering, Ian, if you can tell us about some applications that this would be useful for.
Yeah, so the focus right now of this paper has really just been on the methods and and theory development. I mean, the immediate application would be the project that I talked about last year in multi-view clustering. But I haven't yet tried this out on any applications. But I mean, I think like learning block diagonal structures kind of like is sort of like a clustering problem. So I sort of think of this as like maybe you have some regression problem, but then you want to like there's a clustering problem embedded within your regression problem. So like that, I mean that like that brain example, like I'm sure that if there were, or you know, I'm sure that neuroscientists could come up with examples where you want to, you know, regress on, you know, brain connections where you think that there might be a block structure. But I don't, yeah, I don't yet have an immediate data applications in mind. But yeah, I mean, I'm very interested in that sort of as a next step, actually applying this on real data.
Okay, thanks.
Great. And other question? Any other questions? Yeah, I think it's probably because it's the end of the quarter, so everybody's very exciting about, you know, going for the summers. Okay, so if no other questions for Iain, then let's thank Iain again, and thanks everybody for participating. It's a very exciting talk.
Yeah, thank you very much.
Thank you all, and have a nice weekend.
Bye.